I'm almost 100. No, not years, but episodes. I'm fast approaching that 100th episode, and I want it to be special, and I want you to be involved. So I'm inviting you to ask me anything, and I'll answer in that episode. Now, that episode is going to be coming up pretty soon, so you need to get your questions into me pretty quick. Have a think what your question is, and then would you like to speak to me, or would you like to write it to me? Okay, got a question in mind? Here's how you submit it. You can record me a voice note and send it to me at my email. That's matthew@chemistrymadesimple.net. Or you can record a short message on my website if you prefer, and that's at chemistrymadesimple.net/voice note. I'll be putting that link in the show notes. If you'd rather write the question to me, again, you can use that email address, matthew@chemistrymadesimple.net, or you can send it as a DM to my Instagram @chemistrymadesimple. Okay, so what are you waiting for? Think of the question, pause, write or record it, and send it to me now. Okay, on with the episode. In today's episode, we're going to be talking about reversible reactions and equilibrium. Hello, and welcome to the Chemistry Made Simple podcast. I'm your host, Matthew Macario, and this is the podcast where you get chemistry confident and we take you from point A to grade A. Hello, and welcome back to the podcast. I hope you're well. Today, we're going to be talking about reversible reactions and equilibrium. Firstly, let's talk about what is a reversible reaction. Most of the reactions that you'll have considered up to now are reactions where the reactants react to become the products, and that's the end of the story. That's all that happens. The products just are the products. But it's not always that simple. Many reactions can happen in both directions. That means that once product molecules are formed, they can also react again to become reactant molecules again. And that goes back and forth. They don't stop there. It's going on all the time. These are reversible reactions. Many reactions are reversible. They can happen in both directions. Once the reactants have reacted and produced some product molecules, those product molecules can react again and become reactant molecules. It's not that simple one and done scenario that you're probably used to expecting and considering. So these are reversible reactions. And when we talk about reversible reactions, and particularly when we talk about their chemical equation, you may have already noticed that we often refer to the left-hand side and the right-hand side of the equation rather than the reactant side and the product side. Something else you'll notice in the chemical equation of a reversible reaction is that the arrow in the chemical equation, it usually points from the left-hand side, the reactants, to the right-hand side, the products, is replaced with a two-way arrow. That two-way arrow looks like two parallel lines, and each has an arrowhead on one end, such that you have two arrows effectively, one pointing left to right and the other right to left. It's a bidirectional arrow, and that indicates that the reaction is reversible. It's capable of going in both directions. It will go in both directions. Don't underestimate the importance of seeing that arrow, looking out for it, understanding it, and using it actually. You won't always be told that a reaction is a reversible reaction. In fact, you're frequently not told. You're expected to notice. And one of the giveaways is that bidirectional arrow. You're expected to notice it and to understand that that's a reversible reaction. It's also really important that you use a bidirectional arrow when you're writing a chemical equation for something you know to be a reversible reaction. And you will likely get marks deducted if you don't use the appropriate arrow. Okay, let's think about a couple of examples of reversible reactions. Now, there are many. There are huge numbers of reversible reactions. And these examples are some that you may have already come across or will certainly come across within your syllabus. The first one is the reaction of the Haber process, the industrial process where ammonia is made. That process turns nitrogen and hydrogen reactants into ammonia, a product. But it is a reversible reaction, and many of the ammonia molecules formed will become nitrogen and hydrogen molecules again. They will react the other direction. And of course, when the nitrogen and hydrogen are reformed, they're free to make more ammonia, and it's an ongoing situation. Another example is the synthesis of ethyl ethanoate. You may have already done this in the lab. You've probably at least considered it in the text, in your textbooks or in a lesson. In this reaction, if we're trying to make ethyl ethanoate, we start with ethanol and ethanoic acid, and they react to form ethyl ethanoate and water. Again, it's reversible, so ethyl ethanoate molecules and water molecules will react together to form ethanol and ethanoic acid molecules. And those molecules can react back and forth for as long as the reaction is permitted to continue. Okay, we haven't mentioned equilibrium yet, so we must do so. Equilibrium means a balance in the reaction, a reversible reaction. To achieve equilibrium, the reaction must take place in a closed system. An example would be a stoppered flask. It's a system where all the substances are remaining inside, they're not able to escape, so not even any gases or vapours can escape. And that's really important. If any of the substances are permitted to escape, a balance can't be reached. In other words, an equilibrium cannot be reached. Another important element of an equilibrium is that the conditions must be stable. Temperature needs to be constant. If there are any gases involved in the reaction, then pressure needs to be constant as well. If we start with our reactants, as the reversible reaction proceeds, product molecules are produced. As soon as some product molecules are produced, then some of those will react back to become the reactant molecules. Now, when we talk about reversible reactions and equilibria, you will often hear about the forward and reverse reaction. The forward reaction is the reaction where the reactants, those on the left-hand side of the chemical equation, react to become the products, those substances on the right-hand side. The reverse reaction is the reaction where the product molecules, those on the right-hand side, become the reactants, those on the left-hand side of the equation. Now, at the beginning, as we start our reaction, the forward reaction is the only one occurring at that instant. As the reaction proceeds at the very early stages, the forward reaction remains much faster than the reverse reaction because there is much more of the reactants present than there is products present. As time proceeds, the concentration of the reactants decreases, and therefore the rate of the forward reaction decreases too. The concentration of product molecules increases during that time, of course, and that means that the reverse reaction rate increases too. In stable conditions, there is going to be a point where the forward and the reverse reactions are happening at the same rate as each other. Those rates have converged to match each other. That means the concentration of the reactants and the products are no longer changing. And importantly, that means the reaction is now at balance. It's reached equilibrium. It's important to realise that at equilibrium, the rate of the forward reaction and the reverse reaction match each other. That means the concentrations of the substances present are no longer changing. But it does not mean that there is no reaction taking place. There certainly is both forward and reverse reaction happening at the same time. In fact, one of the most common errors by students regarding equilibria is to assume that when there's no concentration change, when equilibria has been reached, that means that the reactions have stopped. There's no net change, but the reactions certainly do keep going on. In fact, you may have seen or heard the phrase dynamic equilibrium. That dynamic means that the mixture has reached equilibrium and that the forward and reverse reactions are still occurring. Dynamic equilibrium is not a special kind of equilibrium. There isn't any other sort, so every equilibrium is a dynamic equilibrium. Reactions are still happening. And once that balance has been reached, position of equilibrium, as it's sometimes called, doesn't change unless the conditions are changed. In other words, if we disturb the system, we disturb the reaction. If we change the temperature, this will affect the position of equilibrium. It will affect that balance. If we change the pressure, that can affect the equilibrium position too. And changing the concentration of one of the substances present will also change the position of equilibrium. All these scenarios, changing the temperature, the pressure, or a concentration, are disturbances to the equilibrium, and the mixture will need to rebalance and find its new point of equilibrium. Now, if that happens, if an equilibrium is disturbed, we can predict the change in the equilibrium position if we apply Le Chatelier's principle. Le Chatelier stated that if a system at equilibrium is disturbed, the equilibrium moves in a direction that tends to reduce the disturbance. What does that mean? So the system must already be at equilibrium. We must already have reached that balance. And then the system is disturbed. Conditions are changed, such as a concentration of one or more of the substances present, temperature, or the pressure. And then we can expect the position of equilibrium to move. And that position moves because the forward or the reverse reaction will become more dominant than before the disturbance. And whether it's the forward or reverse reaction that becomes more dominant depends upon the nature of the disturbance and the nature of the reaction itself. If we alter the concentration of one of the substances present, we will favour the reaction that reduces the concentration of that substance. For example, if the concentration of a substance on the left-hand side of the chemical equation is increased, the forward reaction will be favoured more than it was previously. The rate of forward action will increase and become greater than the rate of reverse reaction, as the system tends to reduce that change. Over a period, a new balance will be found and the position of equilibrium will be different to where it was before the disturbance took place. How about if the temperature is changed? If the temperature is increased, the system tends to reduce that change. And that means either the forward or reverse reaction will be favoured, whichever is the endothermic reaction. If the forward reaction from left to right is endothermic, then increasing the temperature will favour the forward reaction. If it's the reverse reaction from right to left that is endothermic, then increasing the temperature will favour the reverse reaction. Again, a new balance will be found, and equilibrium will be restored, but at a different position with a different balance than before that disturbance, before that temperature change. How about if we change pressure? This only affects reactions that include one or more gases in their reactants or their products. In that situation, increasing the pressure will tend to move the system, the equilibrium, in the direction that reduces that change. So that means if there's more moles of gas on the left-hand side than the right-hand side of the equation, then raising the pressure will favour the forward reaction because there are less moles of gas on the right-hand side. And that is a way that the system reduces the pressure, reduces that change. Obviously, if there's more moles of gas on the right-hand side than the left, then the opposite happens. The reverse reaction would be favoured. If there are the same number of moles of gas on the left-hand side and the right-hand side of the chemical equation, then changing the pressure doesn't actually make a difference because it's going to favour neither the forward nor the reverse reaction. There isn't a change in equilibrium position that is going to reduce that disturbance. So we talked about concentration, temperature and pressure. How about catalysts? Now, this is a trick question, in my opinion, that often comes up in exams. Perhaps it's a good question. It's a question of your understanding rather than it being a trick, but it's often asked, so do expect that you're likely to see this. Catalysts do not change the position of equilibrium. A catalyst affects the rate of reaction, but it will affect the rate of the forward reaction and the reverse reaction to exactly the same degree. So at equilibrium, the forward and reverse reactions already had exactly the same rate as each other. If we had a catalyst, the forward and reverse reactions will increase in their rate, but the forward and reverse reaction will still have the same rate as each other. So the equilibrium position, that balance will not be changed. Catalysts do not affect the position of equilibrium. All these changes are quantifiable, and to quantify them, we use the equilibrium constant. And that's going to be the topic of our next episode. We'll go into detail about what the equilibrium constant is and how it works and what it tells us about the concentrations and therefore the position of equilibrium. Okay, let's summarize what we've talked about today. We talked about what is a reversible reaction. It's a reaction that can go both from the left-hand side to the right-hand side of the chemical equation and in the opposite direction as well. I said that we need to include the reversible reaction symbol instead of just the straightforward left to right symbol in the chemical equation. And you will be docked marks for not using that. I mentioned a couple of examples of reversible reactions, and I also said that there are many, many, many more examples. I said that it's important to spot when a reversible reaction is taking place. You won't necessarily have that phrase pointed out to you if you're being asked a question in an exam, for example. You need to spot it, and you need to use that bidirectional arrow when you're writing an equation for a reaction that you know to be a reversible reaction, that you know to have an equilibrium involved. Then we moved on to equilibrium. We talked about equilibrium being a balance. It happens when the rate of the forward and the reverse reactions match each other. It's been reached once the concentrations of the substances present does not change any further. We also said an equilibrium can only happen in a closed system and in stable conditions. We talked a bit about disturbing that balance, disturbing an equilibrium by changing a concentration or the temperature or pressure. We talked about Le Chatelier's principle helps us to understand how that disturbance will change the balance, will change the position of equilibrium. And we also said that that can be quantified, and we'll use the equilibrium constant to do that, and we'll talk about that next time. One thing that we said doesn't affect equilibrium, doesn't affect the balance, the equilibrium position, is the presence of a catalyst. That only affects the rate of forward and reverse reactions to the same degree. It doesn't shift the equilibrium position. Okay, that brings us to the end of this episode. Thank you very much for your time listening. I really appreciate it. Thank you for those of you who are supporting the podcast through our Patreon. I really appreciate that. If you have any more questions on this topic, then please do get in touch. You can DM me on Instagram, that's at Chemistry Made Simple, or you can email me, matthew@chemistrymadesimple.net. Thank you for taking the time to listen to this episode. I hope it's been useful to you. And if it has, please consider supporting the podcast at our Patreon. And that's at patreon.com/chemistrymadesimple. Not only will you be supporting the podcast and seeing our updates, but there's also a community element to our Patreon. So you can connect with other students, and also you can ask questions or suggest topics for upcoming episodes too. Look forward to seeing you there, and also to speaking to you in the next episode. Until then, do look after yourself, and goodbye.